One of the most common goals when we are thinking about parametric statistical inference is testing of means of distributions. So when we want to run, for instance, a t-test or a z-test, what we're really thinking about doing is testing the mean of that distribution. Think about this in a one-sample situation here. Now, if we want to extend the idea of testing for the mean of a distribution to the non-parametric case, it requires a little bit of work because we need to think about what would that test actually mean, how would it go about being implemented. One option for doing this is using the Wilcoxon signed rank test, and the Wilcoxon signed rank test can really be thought of as a non-parametric analog to the one-sample t-test. So the one sample t-test is going to be a parametric technique for testing the location of a distribution. The Wilcoxon signed rank test provides a non-parametric counterpart. So what would it actually mean to do non-parametric location testing? In a parametric setting, so if we're running parametric hypothesis tests, we can discuss the mean of a distribution. We assume that the normal distribution has a mean, right? And so we can test what is the mean of this distribution actually equal to. So in our t-test, for instance, we might test the null hypothesis that mu is equal to mu naught. In the non-parametric setting, we do not actually typically discuss the mean of a distribution. This might seem a little bit strange, but part of the reason is that some distributions don't actually have a mean. It's not guaranteed that a distribution has an expected value. Now that's a little bit weird, that's a little bit out there, but it means that if you don't want to make distributional assumptions, or you don't want to make concrete distributional assumptions, then you probably don't want to assume that there's going to be a mean, or at least if you can get around it, you don't want to make that assumption. Now, if we think about what we're doing with the mean, what we're really using the mean for is as a measure of location of the distribution. There are other measures of location, so for instance, the median stands out as a possible option. And so instead of thinking about the mean of a distribution, when we start dealing with non-parametric testing, we tend to think about the location of the distribution. Now, if a distribution has a mean, then the location and the mean can be thought of as similar to one another. If the distribution does not have a mean, then the location will correspond to something like the median. And so in this setting, we can think about the location as being analogous to testing the mean. Any question you want to ask about the mean, you could instead ask about the location, and then if the mean exists, you're asking about it. But if it doesn't exist, you can still say something useful about the distribution. Okay, so we'll discuss the location instead of the mean, the location being the mean or median or so forth. We're still going to use the notation mu, right? And this is to emphasize the point that really we're doing the same thing non-parametrically, right? And so the mu in the non-parametric setting will refer to a location. We can think about it as being very similar to the mean from our parametric setting though. So ultimately, we want to test the null hypothesis that the mean is equal to 0 versus the alternative that it's not equal to 0. Okay? And so here we're testing mu. Mu represents the location. The location is thought of as analogous to the mean. Okay? In this setting, we might also think about doing a one-tailed alternative, right? So testing either the null that it is less than or equal to 0 or the null that it is greater than or equal to 0. All of these can be wrapped up into the same framework. And ultimately, one of the tests that we can do this for non-parametrically is going to be the Wilcoxon signed rank test. So the Wilcoxon signed rank test, or just the signed rank test, it's named after its inventor, who was Wilcoxon, is going to be a non-parametric test of location. So the setup here is going to be similar to a setup you might take in a parametric setting. So we have x1 to xn being a sample drawn from some unknown population. So notice we're not making assumptions about what population this is. We are assuming that it's going to have an unknown location that we denote using the letter mu here. The one thing that we are going to assume about the distribution is that it is symmetric. Okay? And so in particular, we need a symmetric distribution to be drawing from. Now, this is a somewhat restrictive assumption, but it's going to be more general than the assumption we're making for the t-test, which assumes normality. Okay, and so we want this distribution to be symmetric, and then we're talking about the location of our symmetric distribution. Now, if we want to test mu equals 0 versus the alternative that mu is not equal to 0, we can follow the following steps. So the first thing that we're going to want to do is compute all of the ranks of the observations. And when we're thinking about ranks, what we're going to be thinking about is actually ordering our data from smallest to largest. But importantly, we want to order the absolute value of our data. So we take the absolute value of our first data point, take the absolute value of our second data point, all the way up to our last data point, right? So we're just taking the positive value here. And then we want to sort these from smallest to largest. Okay, and so this is ordering in exactly the way that you would think about there being ordering. Then what we do is we assign each observation a corresponding rank. So R1 is going to be the rank of our point x1 here, R2 the rank of x2, Rn the rank of xn rather. When we're thinking about the rank, we're thinking about, well, what position did it actually get put into when we ordered it? So if when you order point 1 here, it is in the 5th position, it is the 5th smallest number, then R1 is going to become 5. If x2 is the 10th smallest number, then R2 is 10, right? If xn is the smallest number, then Rn is 1. And so we go through and we assign each of these a rank. Once we have assigned all of the ranks, and we've denoted these with Ri, then we can compute our actual test statistic here. And so our test statistic we'll call t, right? It's evocative of the t from our t-test here. And to get this, we're going to add up over all of our data points the sign of our data point times by its rank. And when we're thinking about the sign, we're literally thinking about either this is going to be a +1 or it's going to be a -1, right? So we have either a +1 or we have a -1, depending on whether it's a positive or a negative number. So another way that we can think about this is that we want to add the positives and subtract the negatives. And so we can think about intuitively, well, why are we doing this? Right? And if we remember that we're dealing with a symmetric distribution here, and we're testing, is the location of this distribution 0? In other words, is this distribution symmetric around 0? If it is, then we should expect that there's going to be equal chance of drawing small numbers below 0 or large numbers above 0, right? And so if that's the case, if our data should be both above and below 0 at equal rates, then there should be roughly equal ranks that are negatives and roughly equal ranks that are positive. Right? And so if we end up in that situation, then what we should find is that ultimately this statistic that we have right here, our t-value, this should be equal to around 0 if the null hypothesis is actually true, and it will be a positive value if our observations are more frequently large and above 0, and it will be a negative value if our observations are large and below 0. And so we can think about this as sort of aiming at 0. If we get a value around 0, then the null hypothesis seems somewhat likely. Okay, so we find our ranks, we compute our test statistic. Then we can use what we call the signed ranked distribution in order to determine the p-value. So the signed ranked distribution is going to be a named distribution. We can reference tables for the values. We can turn to statistical software for the values. Ultimately, it's going to provide us with the opportunity of actually calculating out a p-value. And once we have a p-value, then we can draw the conclusions that we need. Okay. In order to get this p-value in R, we can use the p-sign rank function. We'll see that a little bit later in today's lesson. Okay. And so in order to then conduct our hypothesis test, we compute the ranks, we compute the test statistic, we find a p-value, and then we draw conclusions in exactly the same way that we did within the parametric setting. And so ultimately, the difference is just coming in the actual procedure that we're following here. Okay. And so it's worth stepping through this process step by step to make sure that each of these is clear. Okay. So the first step is going to be for us to determine the ranks. When we're determining the ranks, remember, we always need to find the absolute values of our observations first, and then we sort those. And once we've sorted them, we can assign them each their rank. And so suppose that we have these data here. Right, so x1 is -7, x2 is -1, x3 is 2, x4 is 5, and x5 is -10. Okay, and so then we can come and we can write these all sort of down here. I'm going to put x1, x2, x3, x4, and x5. Okay, and then we can fill in their value. That's a -7, that is a -1, that is a 2, that is a 5, that is a 10. Okay, and so first thing that we have to do is we have to work out, well, what is the absolute value? And so in this case, we're just looking at our positive versions, right? So that's going to be a 7, that's going to be a 1, that's a 2, that's a 5, and that's a 10. Okay, and then what we need to do is we need to actually rank this from smallest to largest, right? And so then we're going to get a 1 first, and then we're going to get our 2 second, and then it looks like we'll get a 5 third, and then we're going to get our 7 fourth, and then we get our 10 fifth. Okay, so we rank those all in order, and now ultimately we need to assign, well, which of these ranks go to which observation here. Okay, and so then if we want, well, what is rank 1? Rank 1 is going to be where does x1 actually rank, right? And so our 7, if we look at our 7 here, it comes down and gets rank 4, right? So rank 1 is going to be 4. Rank 2 is this -1, right? This -1 actually gets a rank of 1. Rank 3 is going to be the rank of our value 2 here. The value 2 gives a rank of 2. Rank 4 is going to be the rank of 5 here. If we look at 5, that gets a rank of 3. And then rank 5 is going to be the rank of our 10. 10 gets a rank of 5. So then we get a 4, 1, 2, 3, and 5 as our ranks. And so ultimately, these ranks right here are going to be the ranks that we're using to conduct this test. Okay, so we can walk through that again just to make sure that that was all clear. But what we do first is we consider our absolute values. So we get our 7, 1, 2, 5, and 10. We then sort these from smallest to largest. So we get 1, 2, 5, 7, and 10, right? That corresponds to x2, x3, x4, x1, and x5. And then we can fill in the ranks in order here, right? And so we get that rank 2 is going to be number 1, rank 3 is 2, rank 4 is 3, rank 1 is 4, and rank 5 is 5, right? In that order. And so then we have all of our ranks, which can then become input to our test statistic. Okay, so then we can compute out our test statistic. When we want to compute the test statistic, what we do is we take the sign of each of our observations, so either our plus or our -1, and multiply it by its rank, and then we add those values up. Okay, so suppose that we have exactly the same observations we had before, and we have these ranks that we worked out on the last slide. So how do we work out our test statistic here? Okay, well, our test statistic, what we want to do is we want to take the sign of rank or of x1, right? So I'll write the sign as just SGN. That's common. You might also write that as the word sign out, right? Both are acceptable. So we want the sign of x1 times by the rank of 1 plus the sign of x2 times the rank of 2 plus the sign of x3 times the rank of 3 plus the sign of x4 times the rank of 4 plus the sign of x5 times the rank of 5. Okay, so this is what we want to do for our statistic here. And then we can just fill in all of these values, right? So x1 has a negative sign, so the sign is -1. And then rank 1 is 4. So we take -1 times 4 plus the sign of x2 is also -1. The rank of 2 is 1, plus the sign of x3 is going to be +1, times by the rank of 3, which is 2, plus sign of x4 is +1, the rank of x4 is 3, plus the sign of x5, which is going to be negative, times by the rank, which is 5, right? And so then we get all of these here, and we would simply add those up, and that addition is going to provide us with our test statistic. Okay, and so we can walk through exactly this same process here, right? So we're calculating the sum of the signs times the rank. Right? We get our signs plugged in, so negative, negative, positive, positive, negative. Our ranks 4, 1, 2, 3, 5. Plug everything in, we solve that, and we get -5 as our test statistic. So under the null hypothesis, t is going to follow a sign rank distribution, and our observation of t is a -5. Right? And so specifically, t follows the sign rank distribution with n being 5 in this case. Okay, so we have our test statistic is -5. We got that from our ranks. Okay. So now what we do is we compute our p-value. Okay, so in order to compute the p-value, we turn to our null distribution, which is the sign rank n distribution. And the p-value in this case is going to be computed using this sort of formula here. This is going to be our formula for our two-tailed test in this case. And specifically what we're looking at is we're looking at the CDF. So F is the CDF of the sign rank distribution here. So it's the CDF at the negative version of our test statistic plus 1 minus the CDF at our test statistic's positive version -1. Okay. And this is going to then equal the same thing as 2 times the negative version of our test statistic plugged into the CDF. So the weird part about this is, of course, taking F of the absolute value -1. So why do we do this? Well, the important thing for us to notice here is that the sign rank distribution is a discrete distribution. So the sign rank is discrete. Okay. And so specifically, we want that the p-value is going to be, say, the probability that t is less than or equal to the negative version of our test statistic plus the probability that t is greater than or equal to the positive version of our test statistic. Now, the difficulty that we run into is that if we want to express this value right here, we cannot say that this is going to be equal to 1 minus the probability that t is less than or equal to our test statistic, right? That's not true because we have a discrete distribution here, right? So if you take 1 minus this probability, you would actually only get the probability that t is exactly greater than the value on our test statistic, okay? And so that's not the probability we want. We want this probability here. And so in order for us to do that, what we can say is we can say, well, this probability right here, what it is equal to is the probability that t is greater than t minus 1, right? Because if you are greater than or equal to the absolute value of t, then that means you have to be strictly greater than 1 minus that, okay? And now this is going to be equal to the value that we have right here, 1 minus it plugged in, okay? And so this slightly strange p-value that we're looking at here, that's going to give us the resulting p-value. Most often when we're doing our two-tail test, we're going to turn towards this twice the negative value. However, if you're looking at a one-tail test, right, in our one-tail test, then either we're going to want to compute f of t or 1 minus f of t minus 1. Okay, depending on whether we're looking at the upper or the lower tail test in this case. And so in this case, it does matter to be able to divide up our test statistic, but we can typically rely on the twice the lower bound. Okay, so we have our exact setup as before. Thus, we have t is equal to -5, and so the p-value is going to be t times 5, or f of -5, which gives us 0.625. Okay, and so that is going to be our p-value here. Now, how can we actually get this? We can get this in R by taking this somewhat annoying-looking formula. So we get our 2, which corresponds to multiplying by 2. P sign rank is going to be corresponding to f, right? And so then we're plugging in this expression here, -5 over 2 plus 5 times 5 plus 1 over 4, n equals 5. The n equals 5 part, this is easy enough for us to identify. N equals 5 comes because we have our sign rank n distribution. In this example, n is 5. Okay, so that's what is taken care of there. So then the question becomes, well, why are we plugging in this whole expression here rather than plugging in -5. Okay, and so in R, the important thing for us to note is that we actually need to transform the statistic for the p-sign rank distribution. When you see the signed rank test being presented, there are 3 common ways of it being presented. We're looking at the one where you sum up all of the different ranks. Some people only sum up just the positive ranks. Some people only sum up the negative ranks. Turns out that R is only summing up the positive ranks, and so that requires a transformation of our statistic. What we do here is we say the positive ranks are going to be given by our statistic divided by 2 plus n times n plus 1 over 4. And so anytime that we want to plug in to the R function here, what we have to do is we have to take, well, what statistic are we actually plugging in? Divide that by 2, and then add on this term of n times n plus 1 over 4. And so if we look at what we've actually done here, right, we want f of -5. So we take -5 divided by 2, right, this gives us that first term here, plus n, which is 5, times n plus 1, which is 5 plus 1, divided by 4. Okay, and so when we want to plug into R, we have to use this expression right here for plugging into R, and that will give us the correct p-value then. Okay. Now, given that we have to make this transformation, it might be, questionable, why don't we just calculate the other version of the statistic? And that's because in many situations, we're not going to calculate the p-value directly. We're going to calculate an approximate p-value. Okay, and calculating the approximate p-value, it's easier to do from our statistic t. So the exact p-value is going to be able to be calculated for small n. If you have too large of an n, we're not going to be able to do that. If you ask your computer to calculate an exact p-value and n is very large, then that's not going to end up working out. So what can we do instead? Well, we can use a normal approximation. And so specifically, what we have is that the CDF of our signed rank distribution, right, so f of t, is going to be approximately equal to phi being the normal CDF, of t divided by this term here. And so this term turns out to be the variance of our test statistic, right? But it's n times n plus 1 times 2n plus 1 divided by 6. So we take the square root of it all. Okay. And so if you want f of t, then you can approximate that with phi of this value here. And this approximation is going to work better when n is large. As a result, we can write down that the approximate p-value is going to be 2 times phi of, and then we wanted negative t, right? So we have our negative t divided by our standard error here. Okay, and so we'll very often be approximating the p-value using this formula instead, and because of this, this t becomes very natural to use. If you use the other t, then you need to modify in the approximation, and given that the approximation is used most commonly, then that's actually going to provide us with sort of a better result here. Okay, so if t is -5 and n equals 5, then the approximation is going to give about 0.5. The way that we can get this is by taking p norm, 2 times p norm of -5 divided by the square root of 5, 5 plus 1, 2 times 5 plus 1 over 6. Okay, and that's going to give us that 0.5. Okay, this approximation becomes much better as n becomes larger. Right? So it's going to work a lot better for large n settings. Once we have our p-value, whether that's exact or approximate, we can start trying to draw some conclusions. And so the p-value can then be compared against a level of significance, and the conclusions can be drawn regarding the null hypothesis. The conclusions that we're drawing are related to the location of the distribution, which we typically consider to be the median. So if you want to make a very concrete statement, you can make a concrete statement about the median of the distribution, right? In many populations, because we have symmetric data, this is also going to correspond to the mean of the distribution. But again, we want to be careful about not assuming that the mean exists. Okay, and so you can call it the location, you can call it the median. I would avoid calling it the mean if you're testing using the signed rank test. Now, in practice, again, we're going to be using this very similarly to the t-test. And so if you wanted to run a t-test, you can instead run the signed rank test, and it's going to give you this non-parametric version of the t-test. Okay. The only assumption that we're really making about the distribution here is that the distribution is actually symmetric. If this distribution is non-symmetric, then we're going to have issues applying this test as well. Okay, so ultimately, you need sort of a symmetric distribution. It's probably fine if it's not exactly symmetric, but it should be approximately symmetric. Okay. So all of this is great, but there are a few hiccups that can come up. Specifically, what are we going to do if we end up with ties in our data or if we have zeros in the data? So if 2 or more points are tied in rank, then we're going to require a tie-breaking procedure. There are 2 common tie-breaking procedures. The first is what we call the mean rank procedure. And the idea here is that it's going to assign the average rank from all of the different versions that are tied. Okay? And so we can take a look at an example here. Right? In this example, we have x1 being or x2 being less than x1, which is tied with x3. That's less than x4, which is tied with x7 and x6, and then that's less than x5. Okay, and so we go through, and if we wanted to assign ranks in this case, right, we start out with the same type of process, right? So the rank of point number 2 is going to equal 1 because it's alone in its own case here. Now, the way that we have this written out, right, we would normally get that rank 1 is 2 and rank 3 is 3. However, instead of assigning 2 and 3 in this case, what we're going to do is we're going to take the average of their ranks and assign them both that. And so then if we take 2 plus 3 over 2, that's going to give us 2.5, right? And so then instead we say, well, then rank 1 is equal to rank of 3, which is 2.5. Okay, and then similar here, we can go for rank 4 is going to be equal to rank 7, which will be equal to rank 6. Okay, and in this case, right, normally we would be looking at those as the 4th, 5th, and 6th points here, right? And so then we take 4 plus 5 plus 6, divide that by 3. Okay, and so then we're going to get that all of these are rank number 5. And then finally, we can take rank 5 is alone as the 7th data point here. Okay, and so the mean rank procedure, we lay them all out, we average any that are tied, and we assign the normal ranks to everything else. Okay, and so just to walk through that quickly again here, right, we get rank 1 is equal to 1, rank 1 and 3, or rank 2 is equal to 1 rather. Rank 1 and 3 are 2 plus 3 over 2, so 2.5. Rank 4, 7, and 6 are 4 plus 5 plus 6 over 3, which is 5. Rank 5 gives us our 7. So this is called the mean rank procedure. The other alternative is to use the random rank procedure. And this does exactly what you think it does from the name. So when we have tied points, what we're going to do is we're going to randomly break those ties. So in this case, we would look and say, well, x1 and x3 are going to be tied in rank. So we'll randomly choose either 1 or 3 to be the smaller, and then we rank them in that order. Same thing with 4, 7, and 6. We'll randomly order these 3 so that they are ordered, even though they're actually tied in rank here. Okay. Now, there are pros and cons to both of these approaches. The mean rank procedure actually changes the null distribution. So it's no longer going to be an exact signed rank distribution. The random rank procedure, on the other hand, is going to rely on random variation. Okay, and so both of these are drawbacks in some sense. If 2 people run the random tie-breaking procedure, they might come to different conclusions. But if you're using the mean rank procedure, then you have to change the actual p-value or distribution. Now, in practice, most people are going to use the mean rank procedure. And when they do the mean rank procedure, because the p-value is going to change, you need to use the approximation. Okay, and so often what we will do in practice is we'll apply the mean rank procedure, and then we will actually use the approximation. The random rank procedure does not change this distribution, right? And so that can be very helpful for us. It can work especially well when we are dealing with small sample sizes where that approximation might not be very good, but it is going to rely on some extra random chance, and not everyone is happy with that. Okay. So with dealing with ties, we use one of these 2 tie-breaking procedures. When we have zeros, we have similar choices that we have to make. Now, sometimes what people do with zeros is they throw them out of the data entirely. This can create some issues in certain situations. Sometimes it will work fine. If you just have a couple of zeros, that's probably okay to do. However, typically it's going to be better for us to use our signed rank zero procedure. And the idea here is that we take the sign of 0 to equal 0, but we still consider these data points while ranking. Okay, and so we rank all of the data, but then we give the sign of 0 to be equal to 0. And that way they don't contribute to the actual statistic that we're calculating. Okay. Now, this is also going to change the null distribution, right? And so if you have any zeros and you use this procedure, then you're going to end up requiring the use of that approximation once again. Okay, and so again, there's going to be these sort of trade-offs that you make. If you're using software to perform these, it's probably going to be making reasonable choices for you. However, if you are relying on sort of hand calculations, then this will be up to you to make these choices. Okay. In either case, no matter what procedure we've used, the approximate p-values are going to remain the same. And again, to emphasize, if you use the mean rank procedure or you use the sign rank 0 procedure, you need to update to use the approximate p-values because the null distribution is no longer the same. Okay. One other consideration that we might want to make is what happens if we want to test for a non-zero null value, right? So we want to test a null hypothesis that is not the location equals 0. How can we go about doing this? Well, the signed rank test, as we have described, can only test the null is equal to 0. It can't test for the null being anything other than 0. Okay? But what if we wanted to test the null is equal to mu naught for mu naught not equal to 0? Okay? Anytime we want to test a non-zero hypothesis, what we have to do first is transform the data. So we're adding in a step 0 here. So if x has location equal to mu naught, then x minus mu naught has location equal to 0, right? And so the idea is that x is going to have mu naught, right? And so then if we form these new data, which maybe we'll just call y for now, and we take y is equal to x minus mu naught, then that's going to have location 0. And so then we can take all of these data from y that have come by transforming, and we can apply that exact procedure we just talked about here. Okay, and so then testing whether y is going to have the distribution being equal to 0, or the location being equal to 0 rather, is the same as testing whether x has the location equal to mu naught. So we introduce our step 0, we center all of our data here, and then we use these data in the ranked procedure exactly as described. So we rank them, we compute the rank sum statistic, and then they can be computed exactly as before. Okay. So with all of that, we have all of the tools in place to actually start performing this test. Let's see how it works out in practice. So in this first example, a biologist notes that historically, a particular species of plant is growing to be 15 centimeters tall. They wish to test whether a new fertilizer is going to change this. So they observe 9 plants exposed to the new fertilizer, and they grow to the following different data points. They want to test the researcher's hypothesis at alpha equals 0.05. So what are we actually trying to test here? Well, we want to know that sort of on average, the location of these plants, right? So our mu under the null hypothesis is going to be that it equals 15 because that's what it's been historically. The alternative in this case is going to be that it's not equal to 15, right? And so what do we have to do? Well, the first step is going to be to center our data, right? And we'll call that step 0. And the way that we'll center the data is we're going to take each of these and we're going to subtract off 15. Right? And the idea there is that if it is then a negative value, it means that it grew less than 15. If it's a positive, it grew more than 15. Okay. Then we will calculate the absolute values of xi, right? And rank them. And we find all of our ranks here. Following that, we will calculate t, right? And t is going to be the sum of the sign of our data points times by their ranks. Then we calculate our p-value. The p-value is going to be 2 times our test statistic calculated at its negative value, and then we can draw conclusions here. Okay, and so we have to follow through each of these steps in order, but doing so is going to result in us being able to conduct this test. Okay, and so let's take a look at what this looks like in practice. So our null versus our alternative, mu is equal to 15 versus mu is not equal to 15. So we first transform the data. And notice that we get 16 minus 15 gives us our 1. 18 minus 15 gives us our 3. 10 minus the 15 gives us the negative 5, and so forth, right? 17.5 minus 15 gives us the 2.5. And so all of these data are coming from taking these observations and subtracting off 15. And once we've done that, we can now look at just these data, perform our signed rank procedure, testing against 15, or against 0, rather. So the next thing we need to do is we need to go through these and consider just the absolute values and put them in order here. Okay, and so when we're thinking about, well, what are our absolute values, right? The smallest is going to be 0.5, right? And then we have our 1 here, and then we have a 1.5, and then we have a 2, and then we have a 2.5, right? And then we have a 3, and then we have negative 3.5, right? But that's going to become positive 3.5, and then we have 4, and then we have negative 5, which becomes positive 5. Right? And so we've put these all in order from smallest to largest, but only considering their negative values, or their positive values rather. And then what we need to do is we need to assign the ranks, right? And so then we look, okay, well, where is 0.1, right? 0.1 is in the second rank, and so rank 1 becomes 2. Where is 3? 3 is going to come up into the 6th place here, and so rank 2 is 6. Where is negative 5? Negative 5 actually turns out to be the highest rank, and so it gets a rank of 9, right? Whereas 2 goes into the 4th place here, so the rank is 4. 4 is into the 8th place, and so the rank is 8, right? And so on through the rest of the data points here. So we look at where is this actual data point, you find its rank, you record the relevant value. Okay, and so we do that through everything, and we get ranks of 2, 6, 9, 4, 8, 7, 1, 3, 5. Okay, so now we have our ranks, we have the signs, we can actually calculate our signed rank procedure. And so the idea is we're going to sum over all of our observations here. We take the sign of the observation multiplied by its rank and then add those up. Okay, and so we see for x1, we get just a positive sign here, so it will be just the 2. For rank 2, we get a positive, so it will be just the 6. Rank 3 has a negative, so we get negative 9. 4 is positive, so we get our 4. 5 is positive, so we get the 8. 6 is negative, so we get the negative 7. Everything else is positive, right? So then we get the 1, 3, and 5. And if you sum over all of these points here, right, we end up coming to negative 13 is the option, or is the actual result. Okay? And so we have that our test statistic is negative 13, which we computed by first centering the data, finding the ranks, and then calculating out the signed rank test statistic here. So now we need to take this test statistic and turn it into a p-value, right? In order to do so, notice that under the null hypothesis, we're going to be dealing with a signed rank 9 distribution. Okay, so the p-value is going to be 2 times f of negative 13. Remember, we're always taking f of the negative version of our test statistic. Okay, and so we've calculated 13, and so we take 2 times f of negative 13, right? And then when we want to actually work out, well, what is that p-value? We take 2 times our p sign rank, right? N is going to be 9, so that's easy enough. But then we take negative 13, which is the value we want, divide that by 2, plus n times n plus 1 over 4. So 9 times 10 over 4, right? And this is going to give us a p-value of 0.4961. Okay, and so ultimately we find, based on this, that the p-value is going to be larger than our 0.05. If instead we wanted our approximate p-value, we can take 2 times p-norm of what we need, negative 13 in this case, right? Divide that by the square root of n times n plus 1 times 2n plus 1 over 6, and that's going to give us 0.4413. And so there's a little bit of a gap between these two p-values, but they both lead to the same conclusion. In general, what we're saying here is the p-value is greater than the level of significance, so we fail to reject the null hypothesis. There is insufficient evidence in the data to conclude that the fertilizer is actually changing the location of the heights, right? And so we cannot conclude that it's actually different with the fertilizer than with whatever was being done without the fertilizer. take a look at a second example here. In this example, we have a sociologist who wishes to understand the impact of a new social media platform on users' self-esteem. The researcher hypothesizes the users will have a lower self-esteem than the median of 50 on a standardized scale. They collect the following observations. Right, so all of our observations are here. We want to calculate the signed rank sum test statistic using the mean rank tie-breaking procedure. And so here, we don't necessarily need to actually run the hypothesis test, right? Instead, we're just going to be looking at calculating out our signed rank procedure. To do this, we can note that the hypothesis that we're actually looking to test, right, even though we're not going to be testing the hypothesis, it's important because we'll need to be centering our data, right? The null hypothesis is going to be that the location is greater than or equal to 50 versus the alternative that it is less than 50. Okay. And so because of this, we're still going to be centering the data, right? So we'll have taking x minus 50 as our first step, or our 0th step. For 1, we're going to find our ranks. Our second step is then going to be to calculate out our test statistic. If we were running the test at this point, then we're going to be using the p-value as being, say, f of t in this case, because we have a lower tail alternative, right? Now, in this case, because we have to use the mean rank tie-breaking procedure here, the idea is going to be that while we are actually generating out the rankings, right, we're going to be taking our average ranks. Okay, and so we can see how that will actually come together. Okay, so what would this actually look like to perform in practice here? Okay, researcher wants to test the null hypothesis that the location is greater than or equal to 50 versus the alternative that it is less than 50. Okay, so first the data are transformed here. We take 40 minus the 50, and that's going to give us out the negative 10, right? So 40 corresponds to negative 10. 58 minus 50 gives us an 8. We have another 8 here, right? Negative 1, 14, negative 4, negative 18, 0, negative 17, negative 14. And so what we can see here is that we have some different tied values, right? And because of that, we're going to need to be using a tie-breaking procedure. We also have a 0 value here, and so we're going to need to be using a 0 procedure. Okay, and so we ultimately get 0, less than 1, less than 4, 8 is tied, 10, 14 is tied, right? We have two different 14s here, a 14 and a negative 14, less than 17, less than 18. Okay, and so then when you're going through these, right, you're going to get just a rank of 1 here, just a rank of 2 here, a rank of 3 here, but then we would need to rank 4 and 5, and so both of these are going to get a rank of 4.5, right? And then we get 5, and then you would have a 6 and a 7, and so both of these will get a rank of 6.5, and then 8 and 9. Okay, and so we can actually go through and assign out all of those ranks. So we have 1, 2, 3, 4 plus 5 gives us our 4.5. 6, 5, or 7 and 8 would give us our 7.5, 9, and then 10. Okay. So when we actually calculate out these ranks, it's important for us to remember that our rank 0 is going to get a sign of 0. Okay, and so when we plug in our sign for this rank here, when we have our 0.50, we get a 0 plugged in there. Everything else is going to receive either the negative, right? So 40 is going to correspond to a negative. 58, 58 are both going to correspond to positives. 49 is going to correspond to a negative, and so forth. Okay, so we go through all of our values here. This works out to be a value of negative 21. And so then using the 0 signed rank 0 procedure and the mean rank procedure, then we can calculate out this test statistic here. And so given what we've actually been asked to do here, this negative 21 is the value that we're looking for. But we could also take this a step further and actually work out, well, what is the p-value? Because we have used the mean rank procedure, right? We've used mean rank, and because we've had a 0, we have to use an approximate p-value. That's going to be approximated by phi of negative 21 divided by n plus 1, 2n plus 1 over 6, right? The square root of that quantity. So we can get that here. In R, we can take that as p norm of negative 21 over the square root, which gives us a p-value of around 14%. Okay, and so this last part is not required as part of the question, but it's useful to see that in this case, we would have had a p-value of around 14%. Okay. So the Wilcoxon signed rank test is providing a nonparametric test of the location of a symmetric distribution based on the ranks of the magnitudes of these observations. Essentially, what we have here is a test that acts a lot like a t-test, except we can do this without making the parametric assumption of normality. That's an assumption that the t-test actually requires. In the Wilcoxon signed rank test, we get to loosen that restriction so that we just need symmetry. And then from there, we can end up testing the location. Remember, the location corresponds to something that is similar to the mean, but is not going to be exactly equal to the mean, because in a non-parametric setting, we don't know whether our distributions actually have means. Regardless, it can be used in much the same way and provides us with an accurate test that's going to work even if we do not have the normality assumption.